Okay, my name is Yury. I work with Mozilla, and in this talk we will just talk about WebAssembly. We probably create some simple WebAssembly code. We will attempt to execute it in web browser and Node, and there is possibility it can be executed somewhere else. I'll explain why. From my experience and talking to people, some people still don't believe it's fast enough, or they have misconceptions that it will replace JavaScript, and that's where problems are. But we're going to look into that, and I'll show some couple of live demos, and we'll try to run some benchmarks and see. Okay, assembly language for the web. I guess you already heard that there was saying JavaScript is assembly language for the web. And as Yury was talking about time from 2000 to 2010, there was a rise of transpilers and compilers, and everybody was compiling into JavaScript. That's why the term of JavaScript as assembly for the web appeared, because it became target for all complex applications. At that time, we also got mscripting, and mscripting allowed us to compile huge C++ applications directly to JavaScript, then later into awesome.js, which is a subset of JavaScript. Chrome at that time started developing Knuckle, which was addressing problem with performance. And it also was trying to address performance of problem of security. So now we have WebAssembly, and it's not only language, but it's for the web in first place, but it can be run elsewhere. WebAssembly file is a binary file, and it contains your code. It contains some important metadata to describe your code. It may contain some data, and it also can contain some custom information. Since it's binary, and it's delivered as a binary format, it's not really human readable. For that purpose, WebAssembly has text representation which can be human readable, and essentially you can use it as assembly language. You can learn it, but nobody will actually write in that language. So don't worry, you don't have to learn it, but you probably will be able to read it, especially impress somebody. Okay, machine code. When we're talking about WebAssembly, we're talking about machine code. Every operators in WebAssembly were created to match to native CPU instructions for CPUs like x86 or ARM. So basically, translations from WebAssembly to native CPU is really fast. So you just go and translate one command to native command. Though there is no registers in WebAssembly, and it's expressed via operand stack. Though there is locals, globals, and memory. Why they chose stack machine representation is just for code verifications. Basically, when code is loaded and verified in your browser, it's a very simple process, and it takes almost no time. Versus if you're working with JavaScript, there is some time-consuming calculations happening to parse and verify your code. Let's look at simple program. That program contains minimal information it's only one function, and it returns 42. It's not even printing hello world, because to print hello world, you probably need more functions than that. And so you can see in blue, I marked header of the binary file. In green and pink, magenta, there is signature of the function that just say, OK, that function has no parameters and returns I32 as the result. And it corresponds to that function. Though you can see there is only one single operator. It's constant 42. And I underlined them in the code and underlined it in the binary file. You can see it's very compact if you have lots of code, not just functions. OK, how stack machine works. That's how would you calculate golden ratio. There is snippet of code on the right in WebAssembly text. And that's step-by-step execution. So basically, constants place values on the stack. There is operations that takes operands from the stack and place result back. So, any questions? No? OK. Now, how would one convert between binary and text formats? There are tools, of course, and both of them are created by WebAssembly community groups. One of them called Wabbit, second Binarian. There is at the bottom you will see commands to transfer to convert from one format to another one, and they should perform round trip. So basically, if you just execute, you would receive same results. Web browsers are not required. Is not required to support text format. So every time you load file, you're not loading text format. Versus JavaScript, you kind of working with text all the time. With WebAssembly, you will be working with binary format. Though web browsers can display WebAssembly in the debugger in text form, so it will be convenient for you to read and in the future debug. Okay, how would you load and execute WebAssembly? To this time, all 4 vendors added JavaScript API to load and execute WebAssembly files. For that, you would need load binary data, preferably via fetch API, and then use WebAssembly object to instantiate that WebAssembly module. In this example, we instantiation module and call one of the exports from previous example, which were exporting our function as gold, and now we're executing it right here. Same, when so Node is based on some JavaScript engine. And of course, as I said, all vendors added support for WebAssembly. So you can easily do it in JavaScript shells. You can do it in Node as well. So let me. Live demos. Oh, you have to love them. So that's our simple example. can execute, can convert that to binary format. And you can look content of that format via. So you can see it's binary format. If you will attempt to print it, open it in Notepad, you probably will not see any useful information there. We can compile our gold program. And now, as I promised, we can execute and instantiate that. So that's Node version 10. And with that flag, it just allows me to wait on promises. Otherwise, top-level awaiting is not allowed. So how would I load binary file in Node? We can instantiate binary file. How would I instantiate WebAssembly? I have to await on promise. And eventually it will return me an instance and module that would look like JavaScript object, but it will be an instance. This instance would have, at this point, that have exports property where it will contain all your exports from WebAssembly file, which you would see gold there. And if you execute, you would get result of execution of that function. Simple. Same you can do in web browser. So it's as trivial as that. So, as I said, it's all sandbox. There is nothing available, nothing. So there is no access to file system. There is no access to clipboard. You cannot print anything. So for that, you need bring all your functions that will be used within WebAssembly via imports back into your module. In this case, I'm trying to, how that's called? Sigmoid? It's used in artificial intelligence, neural network stuff. It's high math. Okay, but I need exponential function, and it's not present in WebAssembly. It's hard to calculate. I need to get it somewhere. So, and I'm deciding to import it from our execution environment, from web browser. It's simple. We already looked how machine stack works, and you will see additional command, additional text instruction to have import within my module. And I have symbolic name exponent for that. And for my sigmoid function, I added parameter. Okay, how would I pass that function? And during instantiation process, what I'm doing, I'm just adding JavaScript object with math property, and I passing exponent function as corresponding property. The rest of happens same way. So that should work, and it actually works, but you will see what's happening here is when you call sigmoid tries to call JavaScript back. And that's pretty much how people start benchmarking that stuff. And what they find out that it's not really fast. So if I try to execute my sigmoid functions lots of times, ooh, here we go. It doesn't work because I didn't compile it. That's my sigmoid function. And what do I do to compile it? I just that's what's happening when you fail to load valid WASM data. It says fail to load WASM file. But anyway. So you see that JavaScript outperforms WebAssembly. It's not what would you expect. And I just pointed you to a reason. Because what you're doing, you call WebAssembly function, and then WebAssembly function calls back JavaScript. So it's lots of overhead. The only way you can avoid that overhead, do not call JavaScript that much, or you don't call JavaScript at all. If you need exponent function, you compile it for WebAssembly. Write in WebAssembly and compile it there. What I did, I found standard function that is written by Sun Microsystems in 2004. And I repurposed it to execute my sigmoid function. So I just added my header and footer. I compiled that using Clang, which now understands WebAssembly as a target. So you can write C code and compile it using regular C compiler, and it will produce WASM file. So if I'll list. So you will see sigmoid.wasm file right there. If we will try to look content of that file, it will be quite long. So we can just scroll up, down, up, down. There is lots of loops. There is lots of get locals. There is even memory involved. But if we execute that file, I add a parameter. Now you have different story. So your sigmoid function is faster than JavaScript functions. It's not true for every browser, but that's what it's already better results. So instead of 81 milliseconds, you get in 75 milliseconds. Okay. So yes, WebAssembly is fast, but there is buts attached to that. So you have to minimize your calls from and to JS, be efficient. And when you try to pass more complex data structures, it would require you to perform some type of marshalling. So you have to serialize your data into linear memory and then deserialize when you finished your call to WebAssembly. Oh, no. So I was thinking I need to do some live demo, and I couldn't decide what type of demo I should do. And I dive in my memory, and in 2010 or 11, there was audio data API and from Mozilla, and we needed to calculate FFT when we analyze audio signal. So I pulled libraries, and I started I found optimized JavaScript code that calculates FFTs. And it's actually, you can see spectrogram of my voice while I'm talking. So, and you can see that performance, it can do 180 spectrum calculations per second, which kind of enough. You just barely need 44 to do that calculation. But it's all right. We can see it. Optimized JavaScript code can do the job. Then I was kind of skeptical first, and I didn't know where to find good code for FFT for C code. I couldn't find, but well, I found code that written in Rust, so I could use the Rust language. And it was a pleasant surprise that Rust can compile code directly into WASM target, since C language can be compiled to WebAssembly. Rust can be compiled WebAssembly. I said, oh, well, let's try that. So what I did, I wrote a simple file that takes DFT library. I create some globals. And I let my JavaScript code know where this data array located, where my spectrum data is located, and upon transform, I calculated spectrum, and I leave data there. So I was expecting that users of my code will place some data into the data array, and we'll get data back from spectrum. Then I added code to do what I just described, but on JavaScript side. So I took location where data is supposed to be located, and I mapped my float array to that location. I took spectrum location and mapped floats array, and I directly called transform method of my WebAssembly. So at the end, what I got, so it's same functionality, but I can fit twice more calculations into that. What does it mean? It means less CPU is used, less battery life. It's not noticeable. User will not see what's happening, but it will be more efficient for web browser. So all code can be found at ThunderPlains demos at GitHub. I'll add link later, so you can look and inspect and see my thoughts. But that's okay. I already mentioned that I used Clan or C compiler that is part of LLVM to produce WebAssembly file, which supports WASM32 unknown, WASM target. It's going to ship really soon. I think in version 8, they're going to release it by default, so you will have on your computers WebAssembly compiler. You can use M scripting. Mscript from the beginning could support WebAssembly, so you can generate WebAssembly code. Rust always had WebAssembly target in mind. So you write small application, you can bring crates from somewhere else, which is their term for packages. And you can produce small libraries and execute them in the web browser. They also have additional tools to simplify your work. There is Wasm bindgen tool, which tries to wrap all JavaScript objects, and it's trying to perform marshalling of the data for you. You don't have to write all of those get data pointer, map, floats array. Wasm bindgen will do that for you. There is also such libraries as GSSys and WebSys that would help you to write Rust code and manipulate JavaScript primitives like object, math, DOM objects, which is WebSys allowed to do. So you can create DOM elements in Rust, and it will be mapped to the browsers. There is a book for that. As a tool, it was started as a toy, but it got big. There is WebAssembly Studio. It's for people who want to try WebAssembly but don't want to install all of those tools. You can just go to web interface. It looks like VS Code. It's like Web IDE. You can type your C code there. You can build it, and you can run it. You can see same example, but written in C. Executed. You can also inspect what WebAssembly file is produced. There is also Python version that was compiled to WebAssembly. So you can run WebAssembly you can run Python in a web browser. You can try that. I told that WebAssembly is part of almost every JavaScript engines out there. So you can use it, but can it be without JavaScript? Yes, there is plenty of virtual machines, virtual execution environments. There is CraneLift, which is a generator that takes AR, WebAssembly AR, and generates native code. There is also WebAssembly virtual machines that only do is execute WebAssembly. There is interpreter, and there was attempts to build WebAssembly execution environments on Linux, or even just have dedicated microkernel. Mozilla working, in this case, I'll talk about CraneLift. Mozilla is working on that project, and it's already part of Firefox Nightly. You can see its functionality, but it's kind of new monkey, new environment that will allow execute WebAssembly even faster than it's now. Most of JavaScript engine vendors, what they did, they repurposed JavaScript engine to execute WebAssembly. CraneLift is doing from scratch. So they're trying to take WebAssembly, compile to native code, and execute that. The Fastly company that's doing edge computing finds CraneLift very attractive because they need to have fast solution, and they need to execute like thousands and thousands requests per second. And in secure manner, and they want to have execution be more predictable. They finding that WebAssembly can achieve that if they compile to native code. That's pretty much it. They have questions? I know that currently anything that's based on LLVM can be compiled to WebAssembly. That's why I mentioned Rust and Clang. So C, C++, Rust. But there's plenty more languages, and there's additional languages added just specifically to cover deficiencies of WebAssembly text format. So people would like to write WebAssembly code directly and compile it back to WebAssembly. But there is no limit what language would support WebAssembly.
Plans for a GCC implementation as a target?
GCC, I heard something about that, probably. Every WebAssembly right now is treated as additional target to native CPUs. Basically, people target WebAssembly at the moment. Yes.
What does this look like on mobile?
Good question. Today, I tried to execute it on my Android phone. It works in Chrome. It works in Firefox. Of course, it won't. Yeah. I don't have iPhone, but somebody loaned me one. I tried it. It works in Safari. So mobile is supported, I guess. That I don't know about Windows phones. I tried Edge. Edge works. Okay, work on WebAssembly is not done, and one of the main topics is threading. And currently, Chrome team announced support of threads. Firefox had it for a couple of months, and Rust team announced they have kind of wrapped support for Rust, so they can produce binaries that would use that thread feature. But it's a hard topic because it's supposed to be released earlier, but there was Spectre and Meltdown vulnerabilities. That's why it was delayed, and until that subject will be covered. But yes, threads first in the list for WebAssembly. I'm sorry?
What do you do as a next? You told that REST is the first of the week?
Well, there is plenty. All native WebAssembly is trying to cover as many native architectures, platforms as possible, and instructions are selected, for example, to correspond x86 or ARM. There is also such technology as SIMD, which would make calculations way faster. So SIMD is next on priority list. There is support of garbage collector, because right now WebAssembly doesn't let you manipulate and create any JavaScript object. But in the future, it will try to support that in some manner. That's it. Thank you.